All right, so continuing along here with our process of automating the data cleaning or data preparation phase of the CRISP DM data mining process, it's time to tackle outliers. Now, it's difficult, as I've said in prior videos, to automate data cleaning in general. It's easier to automate exploratory data analysis and modeling and evaluation. Data cleaning is tougher to automate because it's so unique to each data set. However, this is one method, managing outliers, that is relatively easy to automate within data cleaning, and so hopefully you'll find this really useful. Now I'm going to break this up into two videos because there are more traditional or older methods for managing outliers where we look at each feature one at a time and make decisions based on just that feature alone. Now this is not as I would say theoretically sound or useful as the newer methods where we can evaluate all features at once based on a clustering analysis and then identify and manage outliers based on a combination of all features. However, these newer methods take a lot of time and they're very processing intensive. And if you have some larger data sets like the Airbnb data set I've been using, if you've been following along with these videos, you know that we've been working through these 4 data sets. Some of them are smaller, some of them are larger. 2 of them we can use, two of the smaller ones we can definitely use with the newer clustering-based method, but this Airbnb and to a lesser degree this airline data set, that because of how large they are, we really have to use these more traditional methods, which are still very good. There's nothing wrong with them. They're just not quite as useful or accurate at identifying outliers, I should say, as the newer methods. So let's start with the traditional methods in this one. We'll apply it to all the data sets, and then we'll make the next video on the newer clustering-based techniques and apply it to as many of the data sets as we can. So I've got these pulled in. I'm going to read them in once more. Again, these data sets are in the description if you need them. Let's start by making I'll call this one DEF clean outlier, and I'm going to call the other one outliers, or I don't know, you can probably think of a better name than I can. Basically, I want to indicate that this is the one at a time method, whereas the other one is based on all features at once. See if you can come up with something more creative than I did here. So several things we need to pass in at once. So of course the data frame that has the outliers, the list of the features that we want to check. And I'm going to include a messages, like I always do, equals true. And then I think we're going to stop right there for this one. So let's end that function statement. Let's return the data frame and start by importing both pandas. And I think, if I remember right, I might be using NumPy in this one at some point too. So I'll grab that one as well. We can delete it later if we don't end up needing it. All right, let's go ahead and loop through our features as usual for feet in features. And once again, let's check and make sure that the features they've listed are actually there. So if feet in df.columns, else if messages print, do our usual feet is not found in the data frame provided. Whoops. There we go. And here's where we will start performing our work. So we already have that bin categories method that we did in the prior video that handles categorical outliers, is a good way to call those, or categorical groups that have low representation. In this case, we're only talking about numeric features. We're handling numbers that are extremely high or extremely low. And so we better make sure that the features that got passed in, we're only doing this with numeric features. So as we did in our last one, let's check if it's numeric, but we'll say if pd.api.types.is numeric dtype, pass in the feet. Okay, we'll skip it otherwise. And let's also make sure that this isn't we could assume that we ran our basic data wrangling function before we ran this, and that we don't have any features that have like a single value across the whole column. Or we could just go ahead and double check one more time and make sure that we don't have anything like that. So you know, I think I want to add some messages here. If messages print, let's say, feet is categorical and was ignored. And so going back to what I was talking about before, let's go ahead and just check and make sure that this isn't something with a value count of 1 or something like that. So in other words, if, let's see, a good way to do this would be df feet.n unique equals 1. So in other words, if there's just one value in the whole column, this is basic stuff we checked for in basic data wrangling. But it'll throw an error if we try to, or maybe not an error, but it'll give us weird results if we get some of these columns in here. So I just want to double check, even though we may have already run that basic wrangling function before. So yeah, that's why I'm adding this in. Let me add another message here, if we got one of those. So this feat has only one value, and we can give them that one value, df feat unique, first item in that list. There we go. So we'll just let them know there was only one value, and so we ignored it if it gets to that point. Last thing I want to check for is we often will dummy code. Well, we always dummy code if we're modeling and we have categorical features, but sometimes these cleaning functions, you might put them in out of order, or you might need to put them in different various orders depending on the cleaning that needs to happen. So my point is you might dummy code before you get to this clean outliers at times. Probably not, but in case you do, I just want to make sure that we don't have any binary features in there. So features that just have 0 ones. So the way I'll do that is I'll say if not, this is not, I saw this used on Stack Overflow. I hadn't seen this all function before, but I really like it. Credit to many people who upvoted it on there. Value counts, which we've used before. I'm going to check that and say index.isIn 0, 1. Essentially what this does is it says if the indexes, which are the value names that come out of value counts, is in, spell that right. If all of the values in the index are in this list right here, or meaning if not all of them are in this list, then we'll continue. Otherwise, else, let me add a message and say is a dummy code 0, 1, or whatever you want to call it, and was ignored. All right, so basically what we've just gone through and done here is set up a bunch of conditions for which we're not going to clean outliers. So we just want to make sure that what we do here only applies to numeric, relatively continuous features. I mean, it's okay if they're discrete, if they don't have decimals, as long as there's plenty of values, at least more than just 0 and 1, I guess is all we're really checking for. All right, so there's a couple of rules we can use to detect outliers when it comes to a single feature. There's the 2-key box plot rule, and then the normal distribution rule, what's empirical rule. That's the one I'm looking for. So I'm going to handle both of these. Empirical rule, which basically says any value that is either less than or greater than, or that is, I'll say greater than 3 standard deviations from the mean, or less than 3 standard deviations from the mean is an outlier. And then we also have the 2-key box plot rule, which is 1.5 times the interquartile range. So that's quartile 3 minus quartile 1. So anything, I'll say, less than or greater than that value is an outlier. So let's implement these two rules. Well, how do we choose which rule is relevant? It depends. If the feature has a normal distribution, we'll follow the empirical rule. If it's not normally distributed, we'll follow the box plot rule. What do I mean by normally distributed? Let's use a skewness rule. And in fact, we could, depending on the rule you want, skew threshold. I'm going to set this equal to 1 for plus or minus 1. Some people like a more conservative rule, like plus or minus 0.5. So I want to make it a parameter that people can modify when they call this function. So first thing I'm going to do here is calculate skewness of the feature, df_feat.skew. And then if that skew is less than the, I'm going to say the threshold is 1, then I better say less than -1 times a threshold, or skew is greater than the threshold. Oh, skew threshold, not threshold, sorry. All right, so if it's less than the negative threshold or greater than the threshold, then we're going to apply the Tukey box plot rule. So that's the criteria that we're meeting right here. Else, we're going to follow the empirical rule. So in other words, these rules tell us what the theoretical min and max should be that defines what an outlier is. So we're going to set up a min and a max variable to calculate that. So in the Tukey rule, first of all, to get the interquartile range, we need to calculate quartile 1 and quartile 3. That's not so hard. Quartile 1 is just going to be df feet, and we're going to call quantile 0.2, oh no, quantile 1, yeah, 0.25. And then quantile 3 is 0.75. And in that case, the theoretical min is going to equal the interquartile range, or let's see, it's going to be quartile 1, technically what it is minus 1.5 times Q3 minus Q1. All right, so here's our interquartile range. 1.5 times the interquartile range below Q1 is the min. So that's what the Tukey box plot rule is. I probably didn't explain that fully before. In fact, there's a nice, what I can do is give you a diagram of it. Tukey box plot rule for outliers. Let's see if I can get a picture of it for you, just so you can conceptualize. Here we go. So here's the interquartile range, median Q3, Q1. This right here is 1.5 times that range. So I go to Q1 and go 1.5 times this range below Q1. Any value below that is an outlier. Similarly, any value above this is an outlier. So this is what I'm implementing right here. All right, back to my code. I got the min, I got the max. So this should be Q3 plus instead of Q1 minus. Okay, so that's all I need. And then I'm going to check anything below this or above that, I'm going to mark as an outlier. All right, now let's implement the empirical rule. So if skewness was within the threshold, then we're going to say the min simply equals, I need to go 3 standard deviations from the mean. So let's first get the mean, feet.mean. The min would be minus, I'll just say df feet dot standard deviation times 3. Do I have enough parentheses? Yeah, I think so. Therefore, the max is plus the mean. Okay, so I'm checking for skewness, automatically determining what the threshold is for an outlier based on the proper rule. Tukey box plot is what we apply for non-standard or non-normal distributions. Empirical rule for normal distributions, we got those. All right, next, I think I'd like to print some messages at this point and just let the user know what we found. So if messages, then let's go ahead and print out, I better make, and I'm going to count up the number of mins and count up the number of outliers below the mean and count up and above the mean. So let's say this is going to be df.loc, df feet, let's see, less than the min, and we want the value for that feature. So this is going to give us the number of rows, or the data frame with all the rows, where the value of this feature is below the min, and it will return the value in that feature. I guess not that we really need that. We just need the rows. Technically, I think I can just delete this. Yeah, because I just need the dot shape 0. So that'll give me the total number of rows that were below the min. All right, so then the max count is the opposite. Those that are above the max. All right, now that I've got those, I'm just going to print out to the user, let them know the feature, put in the feat name. I don't know if I even need the feature. I'm just going to say feat name. Let's say has max count values above max equals, and then let's let them know what the theoretical max was, and then give them the min count, and min count below min equals min. All right, so just let them know how many outliers were found in this feature in a quick printout. All right, that part's easy. We've just identified outliers so far. You're probably laughing at the easy comment. Okay, but let's test this before I get any further. I've kind of written way too much code. I should have been testing as I went along. Let's run this, and let's go ahead and call clean outliers, or outlier. And let's pass in, let's start with the insurance data set. Insurance, and let's say features equals, and let's pass in everything. So df insurance.columns. We'll leave messages to true and skew threshold to 1, and let's just call it. All right, perfect. Let's do some debugging. Unique. Oh, I spelled it wrong. Let's fix that. Right here. Unique. There we go. So here's what it gives us. It's passing through the data frame. It hasn't done anything to any of the outliers in here, but it's simply analyzed each of the columns for me. Let's see, age has only one value and was ignored. Let's see what I did wrong there. I think I got probably a greater than or less than sign wrong. N unique, if df feat n unique equals 1. Well, looks like I'm an idiot. Hopefully you caught that earlier when I was making this. We don't want it to do all this only if it equals 1. I want the reverse of that. If it doesn't equal 1, then I want it to go ahead and check for outliers. If it does equal 1, then I want it to give this error message right there. So I just had my logic reversed. Hopefully you caught that as I was going through earlier and already fixed it, but if not, we got it right there. Let's go ahead and try this again. All right, perfect. This is what I was expecting to see. So age has 0 values above the max and 0 below the min. Age is, if you remember from our very first videos when we were doing automating univariate stats, you might remember that age was very normally distributed. And so no surprise there that we had no outliers. Okay, sex though, categorical was ignored. Perfect, that's what it's supposed to do. BMI has 4 values above the max and 0 below the min. So okay, we got 4 outliers there. Children has 18 outliers above. Children, you know, this one doesn't have a normal distribution, which is fine, but it's also not continuous. It's discrete. I might be a little less worried about this. That means that there's 18 records that have 5 kids. So I don't know. This is why we can make functions with data cleaning that help us, but it's tough to fully automate, because I would look at that and say, no, I'm not really worried about children since it's not a continuous feature. And I might just say df insurance.select. No, what am I going to do here? I could just give it a manual list, or I could say drop columns equals children, and then grab the remaining columns and have it not even try children next time I run it. There we go. So now children doesn't even come up. Smoker and region are both categorical and ignored. Charges has 139 values above the theoretical max. And you might remember this was definitely a skewed feature, so it's using the Tukey box plot rule, which it should right there. All right, well, we've made the function recognize and count up outliers. Now let's make it do something about them. So I'm going to come right here after the messages, And here's where I want to actually clean things up. So I'm going to say if min count, let's see, I want min count and max count to be calculated no matter what, even if we don't do messages. So what I better do is take this messages right here and put it after the min and max count so that this gets calculated no matter what, and only this is printed if messages equals true, because I want to use that min and max right here. If min count is greater than 0 or max count greater than 0. So in other words, if it found any outliers, now we're going to do something about it. So there are several ways, several methods that we can handle outliers. So we can filter out the outliers. We can replace the outliers with the min-max cutoff. We can impute the outliers by deleting them and then predicting the values based on a linear regression. So this is a more advanced method. I'm assuming you already understand what a linear regression is. We use an imputation for missing data, but we can also do that with outliers by deleting the outlier value and then predicting it based on a normal distribution, if that's what we think is appropriate. So I want to make a method that handles all of these, or it does each of them. So let's start with, what we're going to need is, first of all, to pass in a parameter that indicates what method they want to use. So I'm going to have to add up here something called method equals, what do we want the default to be? I'm going to say filter, maybe remove. I'm going to change this to remove the rows with outliers. So let's make the default remove, and then we'll have replace and impute as options as well. So right here, I'm just going to say if method equals remove, and then let's have some elifs. Elif method equals replace. Elif method equals impute. And then we could also, technically we could just leave it as a null too and not impute it. So I'm going to add elif method equals null. So we'll make those as options. And we'll want to have some documentation maybe for this function. We could put it in a comment up above just to remind ourselves that these are our options for how we can clean outliers. So let's go ahead and implement each of these. The remove one's the easiest. This is just going to involve saying, all right, df equals df, and let's filter this where feet is greater than the min. And then let's copy this and do the same where it is less than the max. So that was quick and easy. It'll just simply get rid of them. So I'm going to continue these ones, whoops, so that we can stop and test this right now and make sure it's working the way we expect it. So continue. In other words, this is just a way to not implement anything in those spaces yet. So what we should see, let's see if we have any values here. I think the way I want to do this is let's first add in one more code block, or I'll just move this one, cut that. Let's do df insurance. Let's sort by the BMI column. And the reason why is I want to see, and let's do this ascending equals false. And I want to be able to see, let's just do head so we don't show everything. I want to see the highest BMIs, because remember it told us that 4 of them were considered outliers. So I just want to see what those values are. And then down here I want to call our outlier function. Oh, you know what I'm going to have to do? Let's save this as df top 5 equals just those highest 3. And then what I want to do is call this method and show you what happens to just those top 5. So here's how I'll do that. I'm going to pull it back in each time. Fresh right down here when I run this cell. So pull in the data set. I'm going to set insurance equal to the filtered version of that data set. And let's go ahead and print out df insurance.shape so you can see how many rows get deleted when I run this. But then I'm going to show you these same top 5 rows right here so that you can see what happens to them. And I'm going to do that by saying df insurance.loc, and then I'm only going to show those rows where df insurance.index.isIn df top 5.index. And still to show those same, I guess I don't need head anymore. Alright, so, I gotta run this cell first. Save the top 5. Alright, and I meant to print this one out. Alright, here's what we got. So, the top 5 rows based on BMI, pull in a fresh copy of the data frame, I run clean outlier, and it says, okay, no outliers for age, sex is ignored, BMI has 4 outliers, and then we've got ignored, and charges. So the only thing that, let's see, it should have removed, it gave them to me in a different order again, which is fine, but it should have removed 13, 17 through 116. Let's see what we've got going on here and why that didn't remove those. Yeah, it still has all 1338 rows. So right here, method remove, that's the default. Did I include that? No. Yeah, I never ran this cell up here. That's why I had to rerun my function. There we go. All right, so as you can see, 286 was the only row from here that was below the theoretical max, which was 48.957. And so our remove method worked. It simply filtered those 4 out. But it also went through and filtered out those that were outliers based on charges. There was 138 more there. So 138 plus 4, 142. So that's why we've got 1338 minus 142 rows left in this data frame. Okay, so remove seems to work nicely. What I want to do next, though, is let's try the replace method. Or let's implement replace. So this is where we simply replace the outliers with the theoretical min-max cutoff. That's not hard to do. I'm going to copy these same ones right here, or copy what we used to filter. But instead of filtering, I'm going to say, maybe this was not useful copying those, but it's df.loc, where df feet is greater than the min. Go to that feet and set that equal to the min. So same thing here. I want to say go to every row where df feet is, oh no, I need to reverse this. So this is, on this first one, I want to go to all those. In the one above, I was keeping those that were between the min and the max. Here, I want to go to the ones that are outside of the min and the max. So I got to change this to less than the min, change it to the min, and then here go to those that are greater than the max, and for the column feet, change it to the max. So now this one's going to replace the values with the min-max cutoff. Let's go ahead and I think I'm going to leave this one like that, copy it down here so that I pull the data in again and I can run clean outlier again, but this time I'm going to change method to replace. Okay, let's run these again, see if this works. All right, so keep in mind here we've got, oh, why didn't that one work? This method is remove. It printed out df insurance. This should have still been a data frame with just that top one in it. Let's see what I did wrong here. It is filtering it down, but then it's still showing me all of these right here. oh, this one, oh, I see the problem. This was the top 5 after. I need to go ahead and pull it in again here. After it had already been removed in the cell below. So I'm just going to pull it in again one more time. There we go. Now it'll go down to just one row, just like we had before. And now this one. Okay, so here's what we got. Those 4 right here, 1317, 1070, 1047, 847, 116, those values have been replaced with the theoretical max, 48.95. So see now all these are 48.95. So it trimmed them, or kind of, it kept the rows but moved our values up. This is used sometimes. My only problem with this technique of replacing is that it kind of creates some spikes on our histogram. It makes our distribution not super smooth. Let me show you an example of what I mean here. Once we first pull the data set in, I'm just going to print out here. I have Seaborn as SNS, sns.histplot, pass in df insurance, and x equals BMI. Okay, so here's what it looked like. We had no outliers down here and a few outliers up here. If we run this again after this method, notice it took those extras and kind of added them here to this value. So this value right here, rather than being smaller like it is right here, it added those records up and it made it a bit taller. It worked out okay for now. That's not a bad tale. But sometimes if we have a bunch of outliers, it can make this last bar really high, so that we have a normal one, and then at the end, it pops up high at the end. Yeah, so this is not a bad method in some cases, like with BMI here, but if we were to do this with charges, it would look a bit worse. Let me show you the charges one. So see, charges used to have a long tail. Now all of a sudden we've got this big spike here because 139 values were converted to the theoretical max. So be careful when you use this replace method, although it's a common, valid way to handle outliers. It depends on how many outliers you actually have. All right, last one, or second to last one, is to impute. All right, this one I'm going to try to go through sort of quickly. I'm assuming that you understand linear regression and how we can make predictions. But this one's going to take a few things. So first we've got to import from sklearn.experimental. We're going to import enable iterative imputer. Whoops. Next, from sklearn.impute, import the actual iterative imputer object. Let's create an iterative imputer called IMP. We're going to set the max iterations to 10 so this doesn't go on forever. If it has a hard time converging, random state, no, I'll leave random state off. Come on, don't do that. There we go. Next, I'm going to make a temporary copy of the data frame because iterative imputer only works if there is no missing data. Also, we got to run some of the other functions that we've created to do some cleaning. So I'm going to make df temp equal to df.copy, and then I'm going to run it through our prior, because I need the entire data frame. I need all the other columns to use. I need to use all the other columns to predict the data that's missing here from or the outliers. So I'm going to delete the outliers and then predict those. So to do that, I actually first just realized I better first of all set them as missing. So rather than replace these with the theoretical max and min, I'm going to copy these down here and replace them with np.nan. So I'll clear out the outlier values. So back down here, I'm going to create this temporary data frame with no bad columns so that I can run the iterative imputer and get rid of missing data and other issues. So I'm going to have to call this as, I'm going to call our bin categories function first to handle any categorical values that have too many values. Pass in df temp. I'm going to set features equal to all of them. df temp.columns. So we put a lot of work into that bin categories so that it would handle, ignore numeric features and just handle the categorical ones. I'm going to set messages equal to false because I don't want to run those in here. I'm also going to run, after I bin categories, I'm going to run basic wrangling second. And the reason why I'm doing this out of order is sometimes you might run bin categories and it's possible that it could create some columns that are all others. Who knows, maybe there's all unique values or mostly unique values, and somehow the basic wrangling doesn't catch those. I just learned by experience to run bin categories first, and then just in case it creates a column of all others, run basic wrangling second to catch those. Let's run get dummies now so that we can, because we can't have any categorical features when we're running the iterative imputer. So I'm going to run pd.get dummies. I know I haven't used this method in this video series first, but I'm assuming you've already learned linear regression and you understand this concept. So I'm going to pass in df temp and then drop first equals true. So at this point, we should have no categorical features left, and it should clean up so that we don't have too many sparse values, and that takes care of those with too much missing data, or you remember when we went through that column. I'm not going to go through the details, or when we went through that function. So now all I'm going to do is run the iterative imputer by putting this in a new data frame. Data frame. I'm going to pass in the imputer object and run fit transform and pass in df temp. So this is going to go through and find all the missing values that we just created right here, and it's going to fill all of them in the entire data frame. So all missing values left will be predicted and imputed. And in this new data frame, when it does that, it strips out the column names. That's why I'm putting this in a new data frame, and I have to reset the columns equal to df temp.columns, and then reset the index equal to df .index or dftemp.index. And then I'm also going to cast. I learned by experience I need to cast the results to float. And I think that's it. Oh, lastly, I need to convert the columns. It's going to create a multi-leveled index. And to get around that, I'm going to set df.columns and just reset all of them right here to df temp.columns.get level values, set that to 0. Finally, last thing that we need to do here is set the index to integers. And if you don't, you'll get an error message and you'll see why. But df temp equals df temp.index.as type int 64. Okay. This will create now a data frame, df temp, that has filled in all of these missing values with a predicted value. What I want to do is I only want to save the column that we're currently on. Because if I do that, then I can go through the rest of my columns and predict them one at a time with other predicted values from this column that's been filled in. And I may not want all of this. Like I want this function to only handle outliers, and I don't want to save all of these steps that I've put into the data frame. And so as a last step here, I'm going to save only the column from df temp that we are iterating on in the main loop, because we may not want every new column, for example, created when the dummy codes were calculated. All right, so to do that, I'm just going to say df feet equals df temp, feet. All right, I know that was a lot. Let's run this and see if I've got it all down correctly. So I don't need this anymore. I think I've made the point, so I'm going to get rid of my seaborne chart. I don't need it here either. Let me pull it out of this one. And let me go ahead and add another code block so we can test out this new impute technique. I'm going to show you the difference. So change method to impute. All right. Oh, I got to fit all my other functions into memory. So I'm going to runtime, run before, and then run this one again. So I had, from our very first video, that basic wrangling function. I had to put all those in memory first before it would work. But I think we're good now. All right. So this is run. And here's what we've got. So I want you to compare this to, for example, 1317 in the original data set was a BMI of 5313. That got converted to a null value, and then the predicted value, based on all the other features, was 31.8. So rather than just replacing with the theoretical max, we're replacing it with a predicted amount. And actually, what I should have done is go ahead and shown you the hist plot once again. DF insurance X equals BMI. Maybe even charges would have been better. So notice we don't get that level like we had before when we replaced it with the max. It's got kind of a bit better of a curve to it now still. It slowly goes down. Let's check charges. That was the one that was kind of egregious. So notice charges. No longer do we have that big high bar at the end there like we did using the replace technique above. Let me put it back up here too so you can see it in both. So in this one, we simply turned all of that long tail into the max value and it created that issue. When we impute, it's properly predicting where those charges would have been all throughout the histogram. And this looks a lot better than what we had before. Now, it's still not normal, and that's something that we can fix with some skewness transformations, which we'll do in a later video, but it looks far better. Okay, this has been a long video, and I know this was kind of complicated. Feel free to ask questions in the comments if you're not sure how this all worked, but this function, once again, handles outliers one feature at a time, meaning it doesn't use all features together to predict whether the entire row is an outlier, which we'll do in the next video. But one feature at a time, and it gives us the options to, first of all, it identifies outliers properly based on the correct method, depending on whether or not the feature is normally distributed. And then it manages outliers with one of 4 different possibilities. Oh, this last possibility was nothing more than leaving the values null in case there was something else we wanted to do with them. So I'll just plug that in right there, and I won't even bother testing it. Okay, hope this was useful. We'll proceed with the newer method in the next video.